Here U1 is produced because of the V1. V1 के वजह से E1 प्रोड्यूस हुआ है, V1 के वजह से I1 गया, I1 करंट की वजह से फ्लक्स डेवलप्ड हुआ एंड दैट फ्लक्स linked with the primary and secondary winding correspondingly generating E2 and E1. So this E1 will be in phase opposition with V1. This is also called back EMF of primary. So friends, let me discuss about the most important electrical equipment which is called transformer. Transformer is extensively used in almost each and every sector of electrical engineering. Basic principle of transformer is electromagnetic induction, Faraday's law of electromagnetic induction. If we want to discuss about the principle, the operating principle, so I have demonstrated one diagram here. For example, this is the primary circuit. If we consider it, this is the primary circuit and this is secondary circuit. So from primary to secondary there is a transfer of energy. So transformer means nothing but transfer of resistors or transfers of shifting resistors or transfer of impedance. So basically here we are transferring energy from one source to one side to another side. One fun fact or interesting fact is that transformer don't have any electrical link between primary and secondary. So as you see that the primary circuit, this is connected to primary circuit and this is connected to, this is the secondary circuit, and there is no electrical link but there is a magnetic link in between primary and secondary. So in transformer there is no electrical link between primary and secondary but there is a magnetic coupled circuit between primary and secondary. For example, this is the flux which is coupled by both primary and secondary circuit. Also, as it is a static device, so I will just note it down. Point 1, no electrical link between primary and secondary. Number 2 point, common magnetic link. Although there is no electrical link between primary and secondary, but there is a magnetic link is there. Number 3, no rotating parts. It's a static device. It's a static device. There is no rotating parts in a transformer. All these parts are static device. Hence, there is no rotational loss, only hysteresis loss. That means core losses and copper losses in a transformer. So there is only core loss and copper loss in transformer. There are only core loss and copper loss in a transformer. Now as there is no rotational loss, friction loss, windage loss, there is no rotational losses, the efficiency of transformer is generally very high. The efficiency of transformer is generally 95 to 99%. The efficiency of transformer is generally very high because there is no rotational losses, only core loss and copper losses. Now let us understand how a transformer basically works. So here in primary we have connected V1 voltage source, alternating voltage source. So there will be a current flowing in the primary winding which is called primary current. Let us assume it as I1. Because of this primary current I1, there is an alternating flux phi set up in the core. Now this flux is not only linked with the primary but also linked in the secondary winding. Commonly this is called mutual flux. Please note it down, it is not leakage flux. We are not considering any leakage flux right now, we are considering only ideal scenario. So this flux phi, we are assuming that the primary flux, primary current set up a flux in the core and the entire flux is linked with the secondary, which is not practically possible in the primary. For the sake of simplicity right now, assume that it is an ideal transformer, there is no leakage flux in the transformer, and this phi, mutual flux phi, which is set up by the primary winding, is linked with the secondary winding also. So as this flux linked with the secondary winding also, okay, because it is alternating flux, so any alternating flux in nature, that means varying flux, will generate an EMF d phi by dt. So there will be an EMF generation in the secondary side also, which is called E2. And if load is connected to this secondary winding, there will be current will be flowing through the secondary winding also to the external load. So this is basic principle. Now there is an interesting phenomena happened in a transformer. So as I said earlier that I1 will set up a flux phi in the core. Now this phi flux, we have seen that because of the flux there is a EMF induced in the secondary E2, and if load is connected current will be flowing through this, current I2 will be flowing through this, that means secondary will get some current. Very fine. Now this flux phi will not only link with the secondary but is also links with the primary. So because of that, one EMF will be induced, which is called E1. So as like E2, E1 will also generate because of flux phi. So as per Lenz's law, this E1 will be in phase opposition, will be in phase opposition with V1. क्यों ऐसा होगा? Because Lenz's law state that direction of the induced current will be such that it will oppose the cause producing it. So here E1 is produced because of the V1. V1 के वजह से E1 प्रोड्यूस हुआ है, V1 के वजह से I1 गया, I1 करंट की वजह से फ्लक्स डेवलप्ड हुआ एंड दैट फ्लक्स linked with the primary and secondary winding, correspondingly generating E2 and E1. So this E1 will be in phase opposition with V1. This is also called back EMF of primary. Back EMF of primary. We will talk about it later on. So this is back EMF of primary, and it helps to limit the primary current of a transformer, and that is why transformer does not operate in DC, because there is no back EMF, because there is no varying flux, there is no varying source of voltage, hence the transformer will not operate in DC. So what we have understand is E1 is in phase opposition with V1, or we can write down that V1 is equal to minus E1. E1 and E2, E1 and E2 will be in same phase. E1 and E2 will be in the same phase because both these EMF is produced by the same flux phi. Next is V2. So V2 is nothing but the terminal voltage of the transformer, which is almost equal to E2 if we consider negligible resistance and reactance drop. So V2 is nothing but the terminal voltage which is obtained from E2, That means it will V2 and E2 will be in the same phase. It will be in the same phase. Or we can say that V1 is equal to minus E2. So we can say that E1, E2 and V2 will be in the same phase. E1, E2 and V2 will be in same phase. We can say that. So now let us quickly draw the phasor diagram of this transformer in no load. Considering it is an ideal transformer, let us draw the phasor diagram. Whatever we have learned so far, we will just plot it in a phasor. This is phi flux, this is voltage V1. V1 and E1 will be in phase opposition, so this will be E1, and E1 and E2 and V2 will be all in the same phase. That means we can say that E2 is equal to V2 in this direction only. So V1 and E1 will be a 180 degree phase opposition, and E1, E2 and V2, that means terminal voltage V2, say secondary induced EMF E2 and primary induced EMF E1, all will be in the same phase. As you know that E1 and E2 is produced by the same flux phi, that's why these two are in the same phase, and V2 is nothing but we are obtaining from E2, this is the terminal voltage obtaining from E2, so it is in the same phase. Only V1 will differ the phase from these three. So this is the simplistic phasor diagram in no load. We can obtain voltage E1 is equal to, this E1 will be nothing but minus N1 into d phi by dt. Minus N1, phi is nothing but phi m sin omega t. So minus N1 omega sin omega t ddt of sin omega t is equal to cos omega t. We can write down this cos omega t as sin omega t minus of sin omega t minus pi by 2. So minus minus plus हो जाएगा is equal to N1 omega phi m sin omega t minus pi by 2. So as you can see that this is minus pi by 2. E1 and E2 is lags behind the main flux by pi by 2. Okay. Similarly, we can derive E2 expression also. Now let us consider transformer on no load with losses. So far what we have assumed here, there is no loss in the transformer, but actually this is not happened. So practically reluctance of the circuit, reluctance of the magnetic circuit is never becomes 0. So whenever we are delivering some amount of primary current, portion of it will be used for set up the magnetic flux in the core. So actually this primary current, or we can say, let us assume this no load primary current, I0. This no load primary current I0 has to set up a magnetizing current in the core. As varying flux is set up in the magnetic material, there will be some power losses also. So this current I0 will have to deliver or meet these two components of current. This is also called exciting current. It is also called exciting current, this no load current, because this current is used basically to excite the core, to magnetize the core. This exciting current has to meet two components, iron loss or core loss component or magnetizing component. This is called iron loss or core loss, and another is
very small copper loss.
So what will happen if we draw the phasor of this, considering this I0 with V1? So let us consider that the same phasor which we have drawn. This is flux phi, this is voltage V, either E1 and this is E2 is equal to V2. Now this primary current, no load current I0 will be in quadrature with this flux. This is IM and this is IW. Now this angle phi 0, that means the angle between V1, the primary source of voltage, and no load exciting current I0, the angle between I0 and V1 is also called hysteresis angle. This is also called hysteresis angle. So this phi 0 or hysteresis angle occurs because of the core loss happened, which shifts the current phasor, from V1. I0 is made up of large quadrature of Im, and hence PF of no load is very small, negligibly almost 0.2, 0.3. PF of a transformer at no load is very small. So no load copper loss I0 R1 is very small and may be neglected. So you can write down the active component from here, active component IW. IW is nothing but is equal to I0 and IM is equal to, so this is making cos phi 0, the active component, that's why this is cos phi 0, and IM is equal to I0 sin phi 0. So no load current I0 has to deliver these two component IW and IM. Clear? Now if we want to draw an equivalent circuit of this condition, whatever we have discussed, let's see how it look like. So this is V1, this is I0, no load current. Now this no load current will divide into two parts. One is IW and another is magnetizing component IM. Here we are considering Rx, this is R0, it is R0, that is X0. So one is IW, another is IM, and this is E1, this is U2, this is V2. So this is the no load equivalent circuit of actual transformer considering these losses. Okay. Now so far we have considered transformer in no load condition. Now let us assume that a load ZL is connected. So the terminal voltage is V2, secondary current is I2. So let us consider that load ZL is connected. So when secondary is loaded, secondary current I2 will set up, and this phase and magnitude of I2 will depend on the nature of this load. It will be in phase with V2 if it is pure resistive. It will lags 90 degree by V2 if it is pure reactive. If it will leads V2 if it is capacitive. So the nature of the load will determine the phase of I2. Now remember, during no load, what happens at no load condition, I0 sets up an MMF, primary MMF N1 into I0, which leads to a flux in the core, which leads to circulated flux in the core, and because of that E1, I2, E1, E2 self-induced EMF has been produced, and we have discussed so far. Now when I2 sets up, that means when secondary is loaded, I2 will also sets up his own MMF, set up his own MMF N2 I2. So this is produced by no load current I0, and this is this MMF produced by I2, N2 I2. Now because of N1 I0 flux phi, that is mutual flux phi, has been produced earlier. Because of N2 I2, it will create also a flux phi 2. Because earlier case we have seen that because of I0 there is a mutual flux phi linked with the both the winding phi produced. Similarly, because of I2 there is a secondary ampere turns N2 I2 will produced, and this MMF N2 I2 will produce a secondary flux phi 2. This phi 2 will oppose this main flux. That means this phi 2 produced by demagnetizing ampere turn of secondary current I2, that means N2 I2, will oppose the main flux phi, and it will try to weaken the main flux phi. So phi 2 will try to weaken the main flux phi, and hence primary back EMF E1 will try to reduce. So value of E1 will depends on the magnitude of main flux phi. So if phi 2, that means the demagnetizing ampere turn N2 I2 produced by I2 try to weakens the main flux phi, then E1 will also drop down, E1 will try to reduce. So the difference of V1 and E1, so the difference between V1 and E1 will increases. So if V1 minus E1 is increases, more current will be drawn from primary. So more current will be drawn from primary. That means सिर्फ I0 से काम नहीं चलेगा. There will be some more current will be added to it. Let us this additional primary current is I1. So the net primary current I1 is equal to I0 plus I1 dash. So let us this additional current is I1 dash. Let us this additional current is I1 dash, which is required to balance this effect. Obviously this I1 dash will be in phase opposition with I2, because I2 के वजह से इसका पैदा हुआ. So as per Lenz's law, I1 dash will be in opposition with I2, because I2 is the reason. Because of I2, ampere turn N2 I2 produced, then phi 2 produced, phi 2 weakens the main flux phi, then E1 gets reduced and E1 gets reduced. So the difference of V1 minus E1 gets increases, and because of that additional current will be drawn from primary, which is called extra additional current is called I1 dash. So I1 dash will be in phase opposition with I2. Now this I1 dash is called counterbalancing current. Please remember it. This I1 dash is called counterbalancing current, because this is produced to balance this effect. This main flux weakening effect को reduce करने के लिए इसका पैदा हुआ है, to maintain the original flux density. This I1 sets an MMF N1 I1 dash in the primary. So this I1 dash will produce an MMF N1 I1 dash in the primary, which produce extra flux phi 1 dash in addition to the original flux which was phi. So this phi 1 dash, so now this phi 1 dash will be in the same phase of main flux phi and it's cancel out phi 2. So phi 1 dash will be in the same phase with phi. It will be produced by the counterbalancing current I1 dash, which is produced because of I2, and this produce some extra flux phi 1 dash which will be cancel out the phi 2, and thus from no load to full load the total mutual flux in a transformer remains constant. Hence the flux phi in a transformer remains constant from no load to full load, because as you see that whenever there is a load, we are putting load I2 in a transformer, that I2 will produce an EMF, I2 will produce an MMF which is called N2I2. This MMF or counterbalancing MMF will produce phi 2. This phi 2 try to oppose phi, that means the mutual flux, the main flux of the transformer phi, and it will try to weakens the flux. Thus E1, the value of E1 gets reduced, because if phi weakens, E1 will also reduced. If E1 is reduced, then V1 minus E1, difference of V1 minus E1 will increase, will be increasing, and because of this some extra current will be drawn from primary. Let us assume that this extra current is I1 dash. Because of this extra current I1 dash, it will produce its own flux phi 2, it is own flux phi 1 dash, and this phi 1 dash and phi 2 will be cancelled out each other to maintain the constant flux density in the core. So these are the phenomena happens in a transformer when a transformer is loaded. To memorize it, let us put it in a very simplistic manner. You can copy this whatever I am writing now. So no load current I0, that I0 sets up a flux N1 I0. It is produce main flux in the core, mutual flux in the core. When secondary is loaded, I2 is flowing. So I2 sets up its own MMF in the secondary, that is N2 I2. It creates a secondary flux phi 2. Now this phi 2 weakens the main flux phi, and as main flux is weakening, then E1's value of E1 also gets reduced. So if E1 gets reduced, then the difference of V1 minus E1 will be increasing. So V1 minus E1 will be increasing means more current will be pulled from primary, that means I1 is increasing. So let us that the additional current is I1 dash, which is called counterbalancing current I1 dash. This I1 dash will be producing its own MMF N1 I1 dash, and this will produce an extra flux phi 1 dash. This phi 1 dash and phi 2 will cancel each other. Thus main flux phi remains constant from no load to full load. So this happens in a transformer. Thus phi remains constant in full load. So this is exactly what happens in a transformer when we are putting load on the transformer. Please copy these entire things as I have written in this manner, so that you can memorize it, because to remember it of the entire phenomena is important. So now let us draw the vector diagram of this phi. This is V1, this is E1, E2 is equal to V2, this is I0, and this is I1, this is I1. So this is the vector diagram on load. considering ideal transformer. This is I0, no load current. This is I1. I1 has to supply I1 dash plus I0, as I have said. I1 dash has to I1 has to supply primary current. I1 has to supply I0, no load current, plus counterbalancing current of secondary I1 dash. Counterbalancing current of secondary, that is I1 dash. So this I1 dash and I2 will be in the exactly phase opposition. So that's why it is I1 dash, it is I2. Correct. So this is the vector diagram of transformer on load. Now the concept of leakage reactance. So far we have, whatever we have discussed so far is for ideal transformer, but in actual scenario there is a finite resistance which cause copper loss in the core and voltage drop in them, and also there is some leakage reactance. So that means not all the flux will be linked with both the winding. Few flux will be considered as a leakage flux. Actually leakage flux is nothing but flux which is either linked with primary or secondary, but not with the both. That is called leakage flux. Actually either with the primary or secondary, it will link either with the primary winding or secondary winding, but not with the both. That is called leakage flux. So now there is some leakage flux in the in practical. There is leakage flux also in the core, and there is some finite resistance also which cause voltage drop and copper losses in the winding. So let us assume that the primary leakage flux is phi L1 and the secondary leakage flux is phi L2. We also consider primary resistance as R1 and secondary resistance as R2. Let us write the V2 equation. So what will be the V2? E2 minus, so V2 is nothing but E2. Let me draw R and XL over here. So let me draw R1 X1, R2 X2. So we are considering that primary winding resistance and reactance is R1 X1, secondary resistance and reactance as R2 X2. So let me rewrite this equation. V2 is equal to E2 minus I2 R2 and minus E1 is equal to, because E1 is in phase oppositions, that's why I am writing down minus E1. Minus E1 is equal to V1 minus I1 R1. Now this phi L1, it will produce E L1. This primary leakage flux phi L1, it is created by I1, so it is in phase with I1 and it produces self-induced EMF EL1, and EL1 it must lags the current I1 by 90 degree. This is called reactance voltage. This is called reactance voltage and denoted by minus I1 X1. This is called reactance voltage and it is denoted by minus I1 and X1. The component of line voltage that balance this EMF is plus I1 X1. Plus I1 X1. We can say X1 is equal to EL1 by I1 is equal to 2 pi F L1 X1 L1 I1 by I1 is equal to 2 pi FL1 is equal to 2 pi FL1. Similarly for phi L2 also, there will be some X2 and X2 is equal to EL2 by I2 is equal to 2 pi f L2 I2 by I2 is equal to 2 pi f L2. So similarly for phi L2 is also we will get 2 pi f L2. So you can note down that the applied voltage V1 has to meet I1 R1 and I1 X1. So if the V1 have to meet I1 R1 plus I1 X1 drop. Similarly, E2 has to meet I2 R2 and I2 X2, these two drop. And flux phi is constant throughout the entire irrespective of load. So what are the conclusions we have drawn from here? V1 has to meet I1 R1 and I1 X1 drop. Number 2, E2 has to meet I2 R2 and I2 X2 drop. That means resistive and reactive drop. Useful flux phi is constant from no load to full load. Useful flux phi is constant from no load to full load. So these are the conclusion we have drawn. V1 has to meet I1 R1 and I1 X1 drop. E2 has to meet I2 R2 and I2 drop, and useful flux phi remains constant from no load to full load.